Okay, my name is Tim Mattson, and I'm going to talk to you about a project I'm really excited about, PyOpenMP, PyOMP. I guess PyOMP is how we often pronounce it. Now, when I was asked to submit, the abstract and title, I was asked to give a logo. And you can see at the top corner the logo I submitted. My colleagues in this project, Georganikoklis, I might always mispronounce his name. Todd Anderson and Stuart Archibald hated it. So they came up with a different logo. And that logo is okay. The first the first part, this meeting's being recorded. Okay. Why can't I advance my slides? There. Okay. Yeah, the hardest part of the whole talk is the first transition. So and we're gonna get all of these admits the whole way through. That's great. Okay. Um, so at any rate, they didn't like my logo and came up with a different one. So this is the one they came up with. So at any rate, off we go. And I am, gosh, okay. I am probably best known for my work on OpenMP. Is as far as I can figure out, I'm the last one of the original group that started OpenMP way, way back in 1996 who are still active. And it's because I think I lack imagination and can't find something better to do with my life. And so, OpenMP is a set of compiler directives and library routines. And the key is our goal originally was to make writing parallel code as simple as we could. We lost sight of that goal. I think OpenMP, in my opinion, I'm very vocal to the fact they've let it get way too complex. But that's okay. Most people ignore the complex parts and only use the simple parts, and that's cool. So at any rate, yeah, to make it as easy to write multi-threaded programs, and we worked with God's languages, Fortran, C, and C++. Now, over time, we went beyond just straight multi-threading, added features on non-uniform memories, vectorization, and GPU programming. And it's interesting. I've been involved with some research on artificial intelligence to generate parallel code. And to support that, we created this open data set, HPC corpus, and basically scanned GitHub and built this massive data set from all the repositories that had last updated dates between 2012 and 2023. And you can see, just millions of C files, millions of C++ files, nowhere near as many Fortran files because it's not as popular these days. But what's interesting is as we built this set, and I'm having continual problems controlling the system, um, we got this data point. Because you see, when you design programming languages, you really have no idea how many people are actually using them. And so this is the first case I'm aware of where we get this general idea of how much people are using different parallel programming models. And what you can see from this is that OpenMP is number one. Yeah, I'm really excited. I did not expect that. I expected among parallel programming APIs, I thought MPI would be number one. But no, OpenMP is number one. And I want to be careful here to point out that we may have had a sampling error that undercounted CUDA. So unlike some people, I like to be very, very honest with the weaknesses in my data set. But at any rate, I'm proud of that. Yeah, OpenMP is very, very heavily used. Now, I don't know any of you. I don't know your backgrounds. I don't know any of that. So I have to say a little bit about OpenMP. So I'm going to say very little, but I am going to say something about OpenMP and what it is. So on the CPU, it's all built around the fork join patterns. You have an initial thread that comes in, and when it needs more threads, you create a team of threads. And the goal with OpenMP is to do everything through as much as you can through pragmas. The idea is you tell the compiler, on my behalf, create this team of threads. So in my C or C++ code, I'd have pound pragma, OMP, parallel. Now, where things get interesting is, okay, how do I work with those threads I just created? the most general and among hardcore experienced OpenMP programmers, they make heavy use of the single program multiple data design pattern, which interestingly enough, this is how you write MPI code as well. So for HPC people, this is like, well, yeah, you replicate the body of code that so each thread is running the same code, and then you use what your ID is and how many threads there are to figure out how to split up the work and decompose the data. And so I have these runtime functions that OpenMP provides to get the thread ID and to get the number of threads. But the other way is an awful lot of code in scientific computing is loop driven. So why don't we just put a pragma in front of a loop that says take the loop iterations and split them up between the threads? And so for an awful lot of people, OpenMP is pound pragma OMP4 will bind to the surrounding team of threads and split up that loop. And you can combine them. So you can go pragma, OMP, parallel 4, and create the team and split up the loops. And we can do reductions and we can control which variables are private to threads and which are not. There's other clauses. The thing is, if you do loops and you do explicit control, you lose a lot of dynamic parallelism features. And not every iterative control structure that you need is a loop. So you need more flexibility. And so this is where we added task parallelism. So I can say, here's one thread that's going to build everything that's inside the pragma OMP single. It's still all inside a parallel, so I'm binding to a team of threads. And then I can create explicit tasks and synchronize with task weight. So this is one slide to summarize, and this really captures an awful lot of what people do on a CPU with OpenMP. Now, on a GPU, the challenges are that you need to take work from the CPU and offload it onto the GPU, and then you need to manage data movement between the host and the GPU. So here I have my generic GPU picture where it has 4 cores. I'm going to say it every chance I get until the world changes. The way my good friends at NVIDIA define core is incorrect. A core is defined as an instruction sequencer. It's a word that's been in use for years. So this is a 4-core GPU and a 4-core CPU. Every time you hear someone misuse core and refer to a SIMD lane as a core, you need to verbally correct them on the spot, and eventually people will get their act together and stop misusing the word core. So this picture shows us a 4-core GPU. In the GPU world, these are called compute units. And in this case, because I didn't want to make the font too small, there's 16 SIMD lanes or processing elements per core, so it is a warp size of 16. Of course, in our video, the warp size is 32, but that makes things too itty bitty, so I didn't do that. And at any rate, whether you're using OpenMP or SYCL or for the most part even CUDA, you're still basically taking in some structure, in our case, a loop, and you're defining an index space. And this is the power, the brilliant power of what people came up with when they designed CUDA, and it's had a huge impact across all these other programming models today, is you define an index space. In this case, it's I define 2 loops. And then I'm going to map the instances of the loop body to each point in the index space. And the powerful piece of this that makes it GPU programming so much fun and so effective is you align your data around that same index space. So thinking about the indices, which are the IDs on your work items, or if you're going to use those awful words, CUDA threads. I say awful because the word thread's already established. You know, we need to fight for the effectiveness of our jargon. And when we repurpose terms too much, we can't communicate anymore. So we have work items, which is the work we assign to each point in the index space. We align our data around that same index space so I can reason about device memory and execution for optimizing my code. Very, very powerful. And then my my unit of scheduling is blocks of these work items called work groups or thread blocks, if you want to use the CUDA terminology. And they're scheduled to run, so all of the work items in a work group are resident and making forward progress at once on the GPU. So now you know GPU programming and life is good. So I'm an old timer. I've been involved in high performance computing since 1980. Oh my God. And this is a picture of my very first parallel computer. It's the Cosmic Q. Chuck Seitz and Jeffrey Fox started work on it and developed it in 1981. I started using it in 85. So yeah, I'm an old timer. Okay, so what do old timers think of Python? Well, there's a paper, there's plenty of room at top. Charles Leisure and a group published it in Science and gets a lot of attention. But I think it really summarizes what old timers think of Python. It's a joke. If you look, if you look at the fraction of peak, I love it when you round it to the number of significant figures. Python on this matrix multiply routine gets 0% of peak performance. And this is why old timers like me traditionally just sort of say that no one who's serious about high performance computing would ever use Python. So Python's stupid and it's just ridiculously slow. And this is what old timers think of Python. And why is it so slow? It's actually interesting to step back and think about why Python is just so uselessly slow. Um, and a lot of the flexibility and what makes people love Python so much is it's dynamically compiled. You don't have to declare data up front because it just on context dynamically figures out data. So the data types and all those such details. So you have your source code, the compiler will check the syntax and generate the bytecode, but then it will interpret it line by line of the bytecode to execute on a virtual machine, which translates into machine code. And to make things even worse is gosh, I don't know. Do I have to click admit? I just want to get rid of it. To make things even worse, in order to make everything thread safe by default, Python has this thing called a global interpreter lock, or the GIL. And what it does is it says that only one thread at a time can make forward progress. Now, this is great for thread safety. I'm going to tell you, I believe the Python people made the right decision because thread safety and getting correct answers is better than speed. But it makes me worried as there's all this talk about how we get rid of the global interpreter lock because it'll open up all sorts of hidden under the covers errors and race conditions. But right now with Python, by default, only one thread at a time is allowed to make forward progress. Yeah, great. What that means is no parallelism built into Python. It's slow. It's a mess. Um, but it's popular. And I just pick one measure. You can bring up measurements of popularity. All the big ones show that for direct programming, Python's number one by far and increasing. And the languages old timers like me love, like C and C++, are slowly going down. And the language that I started on and will dearly love to my dying day, Fortran is so infrequently used, it doesn't even show up on this list. It's nowhere in the data set. So Python's great. And so I really, I look at old timers like me and I say, we got to stop being such arrogant snobs and just recognize that programmers have chosen. They've chosen Python. And if you look at statistics on what people are learning in school, they're learning Python. So we got to get over ourselves and recognize that we have to do and participate with the Python community to make Python a first-class HPC language. And so, yeah, the best way to bring parallel computing to the masses then is to take the number one parallel programming model, OpenMP, with the most popular programming language, Python, and create this combined binding, PyOMP. And because the slides will be available so you can look up these references and track them down, here are the three papers that define the work behind our definition of PyOpenMP. So let's dive in more details. So if you're going to do it right, there are three design criteria a properly designed binding of OpenMP to Python must allow. It must be Pythonic, and that is a word for those of you who aren't really deep into Python. Yes, is it Pythonic? Is it consistent with the styles and philosophies behind the design of Python? So you got to be Pythonic. And I've seen some brilliant work I've been involved with in the past where they tweaked the Python syntax. Python insiders like doing that sort of thing. I think that's a huge mistake. No, no, don't do that. So it can't change Python syntax. So we have to figure out how to fold OpenMP into Python without changing its syntax and in a way Python programmers are comfortable with. It must deliver performance that's on par with what I would get from C and OpenMP. In other words, I have to figure out how to get the same performance or similar performance out of Python that I would get out of C and C++. And it must be ubiquitous. I mean, it must be possible for it to be everywhere and easy to install on all the platforms. So let's walk through PyOpenMP and look at each of these design criteria. So let's start. It must be Pythonic. And gee, because I'm a musician, I always have to have some musical notes around. So we're going to do a discussion of Pythonic OpenMP, and it's going to be in three-part harmony. And if I were a singer, I would start singing now. And yeah, anyway, no, I won't. I'm a guitarist. So anyway, we we get the Pythonic OpenMP by closely interacting with the Numba community. And if you're not familiar with Numba and you play with Python, you need to get familiar with Numba. It is an incredibly powerful, it's not a tool, it's a compiler ecosystem. It's really powerful. We'll say a little bit more about it. But we work very, very closely with Numba, which is a just-in-time compiler. So by the time our code is running, it's JITted into LLVM, which means we get around the GIL. So we get around the global interpreter lock in a very disciplined way through Numba. People doing scientific computing in Python, they use NumPy. NumPy is a package in Python. It has an array type and a collection of common operations over those arrays. So we're very, very much lined up around NumPy. And then, of course, we need OpenMP, but how do we import OpenMP into Python? And you're going to see examples, but we do it using a context manager, which is controlled through a syntactic element called a with statement. You'll see it in a moment. It's coming up. So this is where we are. Let's go. And I'm going to use the famous Py program as an example of the syntax and usage of PyOMP. And I assume you've all probably seen this program. Define a step size. I'm going to do the numerical integration. So I have a loop there and a loop over the steps. And then I multiply by the step size when I'm done. So I do a reduction into sum, then multiply by the step size, and I got pi. And geesh. Okay. So here's what the PyOMP program for PyOpen for the PyOMP program looks like. So I'm going to import the JIT from Numba as njit. And then I'm going to input the OpenMP inside Numba. So we had to modify internals in Numba. And it's going to import the context manager. Remember, that's what the with statement acts is it's a context manager. And it's going to import it as OpenMP. So then I take my function and I decorate it with the njit decorator. This says, do this function. First time you see it, do a JIT compile, cache that JIT compile. So next time you see it, you can just pull it out of the cache and you don't have to recompile it. Every other one of those lines is exactly the same as I started with. The only thing I did is I added with OpenMP, and then this is the key. In those parentheses is exactly the string, as a string, exactly the parallel, the directive from OpenMP. So if you know OpenMP and you know a little bit of Python, then you know PyOMP. We're done. You can leave now. So with OpenMP, the directive, and it just works. So I'm saying give me parallel says give me a team of threads. For says there's a loop coming up that we're going to split up between the threads. Private says X is inside each loop iteration. It's local to each thread. And then I do a reduction over sum using the plus. So I'm going to reduce into sum. Each thread will have its own partial sum. It'll accumulate. And then at the end, it'll put it together to give me a final sum. So that's it. Now, I want to say a little bit about data management. This is the one thing that OpenMP programmers will find a little odd. Because traditional OpenMP programmers are working in languages like C, C++, and Fortran, where you have to declare variables before use. And in Python, a lot about your variables are declared dynamically, including their scope. So basically, if a variable appears outside the block of code managed by the OpenMP context manager, either before or after, it is treated as shared. But if the variable appears only inside the loop, then it is private. So I didn't really need to put private X there. By default, it would be private. But this is just something I do in my OpenMP programming. I add the clauses defining the scope of sharing, if nothing else, as a reminder to the reader. So at any rate, that's it. It's really delightfully simple. And then I can also do the single program multiple data pattern. So as always, I have to, import ngit. I'm going to use NumPy in this one, so I'm going to import NumPy as NP. And now here's the two things that are new. If I'm going to use, so I have to have the context manager. So from numba.openmp, import OpenMP context as OpenMP. Yeah, that's one of those things at the top of all my PyOMP programs. But then I need to import explicitly the runtime functions I'm going to use. So I have import the OMP get thread num because I'm going to need that the SPMD pattern, and I need to know how many threads there is. OMP get num threads. So off we go. So now I have, and for the lack of time, I'm not going to go through this line by line like I did with the other one. You will have these in a slide form, so you'll be able to study them as much as you want. But this is the standard SPMD single program, multiple data approach to solving the Pi program. You know, I need to create my parallel context. Notice here with the context manager, so with OpenMP, parallel. Because I like being clear on data sharing, I have a shared clause, which tells me which variables are shared between outside the context and inside, and same thing with private. Then inside, I pick up my thread ID. I'm going to have one thread. That's that with OpenMP single. It says one thread does this, everyone else waits. So one thread is going to get the how many threads there are. And then I do the loop and I accumulate my local slum. And then when it's all done, I store that in an array that I declared up before the context. And then I sum that array using NumPy. That's the np.sum. And I multiply by step. There it is. It's really cool. Very Pythonic. And I have the single program multiple data. Tasks, if you've never seen them before, you're probably not going to learn them by just staring at this slide. That's okay. I want to mention it that the PDF of these slides will be available, and in an appendix to the PDF of these slides, I have a tutorial introduction to OpenMP with PyOMP. So for any of you who are completely new to OpenMP, and this is like way too fast to master OpenMP, Don't worry, the backup of these slides has a slow, methodical coverage of each of these examples. So in tasks, you create a task explicitly, you put it on a queue, and then threads waiting at a barrier will do the work off the queue. And so this is a recursive parallelism divide and conquer algorithm for doing the Pi program. So you can see over on the right side of the screen, I create my team of threads. That's the with OpenMP parallel. And then I have one thread, that's the with OpenMP single. I have one thread start the recursion, you know. Now with single, it says the one thread of the team that encounters the single will do the work. The other threads will wait at the barrier. So they'll wait until the single is finished. So now I have a whole bunch of threads in the team just sitting and waiting for something to do while one thread starts the recursion. So then the way you read this is I have my recursive function. So now we're on the left side of the screen. And it first checks, am I small enough that I should just do the work? That's where it looks at how many iterations, n finish minus n start. And if that's less than some minimum size, then it just does the work. That's the solve phase of the divide and conquer. If your number of iterations is greater than that, then I'm going to create a variable I'm going to split it basically. So one thread will do one half. I'm sorry, one task will do one half, another task will do the other half. So that's where I have someone equals recursively call this same function. Another thread recursively call this same function. Then I wait until they finish with the task wait, sum them, and then I'm done. So it's really, really cool. And then I just want to mention it briefly. We're going to come back and say a more detailed example we're going to walk through with GPU programming. But this is one thing that I am phenomenally excited about with OpenMP in general. And the fact that we've got it in Python is really wonderful. So to create a GPU version of this code, all I need to do, look, that code is almost identical to the original serial code. All I had to do was say I'm using the OpenMP context manager. I want you to JIT this. And then the single directive is with OpenMP, target, that says offload to the GPU, teams, that means I'm going to run work group by work group across a collection of compute units. Loop, that means I'm going to define my index space from the following loop. And then I'm going to do private X and reduction just as before. This code would run on a GPU. So what could be easier? And when I look at amazing products, you know, I tease NVIDIA a lot, but let me just say Grace Hopper and the direction that's taking architecture is fascinating. And it's going to make it extremely important that whatever programming model you use, you can jump back and forth between CPU and GPU because they've merged tiles of CPU, ARM cores, with their GPU. It's a phenomenal device, and it's going to have a lot of importance. So being able to handle both in one API is very important. So going back to our requirements, I think we knocked it out of the park. We're very Pythonic. Wait a minute, I'm going to give us a check minus. And the reason is there's a style of programming where all of the work is done through NumPy arrays. And the way you have to work with that is you have to outline those arrays into an OpenMP interface into LLVM. But to make it really work, you have to fuse the arrays and then align extra storage. Now, from a computer science and engineering point of view, we know exactly how to do that. We've done that before in other contexts. We just don't have the engineering resources to implement it. And until we do that, I'm not going to take the minus off that check. But I've been assured that most Numba users expect to use the loop, and they're going to be very happy with the loop-oriented approach. So what about performance? And I have to speed things up here, and I apologize for that. Now I'm going to go a lot faster. I'm sorry. But let's talk about performance. And I want to emphasize it does the JIT and caches it. So in all of my performance numbers, I do not include the JIT time. And because in an HPC code, you tend to call a function again and again and again. So you amortize that JIT overhead. But full disclosure, I am not including the JIT time. And so when I look at all those Pi programs, I compare the PyOMP versions to the C OpenMP versions. And as you can see, we're in the same ballpark. We're darn close. And granted, these are very, very short run times, so any kind of excess overhead is going to show up for these slow run times. So, but I'm comfortable saying that, yeah, for this, we got pretty darn close. When I could look at the C program running on one thread, it's on the loop. It's 0.444 with PyOMP, it's 0.447. And I'll be honest with you, since it's one thread, that tells you what Numba can do. I hope one of the lessons you take from this talk is if you're not using Numba and you're a Python programmer in the sciences, you better start using it. Numba is really that powerful. But as you can see, as we start adding threads, we speed up nicely and we're in the same ballpark between the C and the OpenMP. And that holds for the loop pattern, the SPMD pattern, and the task pattern. So yeah, that's really cool. But these runtimes are very, very short. And to be interesting, we need something more involved. And so going back to my original Python's a joke slide where I looked at matrix multiplication, let's look at matrix multiplication. So I have this program in Python with OpenMP, PyOMP. I have a version of it in C, and I'm going to compare them. And it's just a straightforward matrix multiply. I didn't do any of the fancy stuff, the cache blocking and all the various ways you can block and restructure and vectorize. I didn't do any of that. So this is just literally the straightforward code you see before you. I swapped the loop so it's not IJK, it's IKJ. That's like parallel programming matrix multiply 101. Everyone does that. So, and I won't go into the details, but it's if you want to talk about memory architectures, that's something you always have to do with matrix multiply. So I did that here and I did that in the C. But then it's just, parallel for private J and K. Gee, what could be easier? Um, and look at the performance. Once again, I do not include the JIT time, and the JIT time is significant, all right? In this case, on this system, which was a Xeon 5, the JIT time is 2 seconds. So JITting's expensive. But remember, you can do it once and it caches. You can even tell it to cache the JIT in the file system. So if you know you're going to run the same program again and again and again and again, you can even cache the JIT so that it's stored from one run to the next. So if you ignore the JIT time, as you can see, this is comparing PyOMP in green and C with OpenMP, and I'm plotting gigaflops, so higher is better. And then I have little error bars, and I did all the fancy statistics. And, basically they're very, very similar. So I'm extremely excited about the performance we're getting. When we saw it with these numbers, when we very, very first, long ago in 2021, when Todd Anderson and I started this project, and we saw that we were matching the C with OpenMP, we were shocked. It was much better performance than we ever expected. Now let's shift gears and look at the GPU. And to do that, we need something more involved. And I'm going to use the heat diffusion problem. And just because I'm a purist and like math, there's the discretization of it. And it's a stencil code where it's a 5-point stencil. And I'm going to do it over a series of time steps. It's the classic relaxation algorithm where, I run over a range of steps, I do the solve, and then I handle the synchronization between reads and writes by having 2 pointers. So I'm doubling my memory overhead, but I just swap the pointers so that what was utemp, the block of memory pointed to by utemp, and the block of memory pointed to by u swap in between calls to solve. And the more interesting part is if we look at solve. So there's the solve routine. And once again, it's the standard heat diffusion equation solution you all were probably exposed to in elementary school. And when I run this in Python on a Xeon chip, it took 67.6 seconds for 10 time steps with a very, very large, with a very, very large grid. So then if I just, gosh, there it is. With OpenMP, target loop collapse 2. So I want to have a two-dimensional index space. That collapse 2 does. It says take the I loop and the J loop and use them to create that index space that I'm going to map work and data to. And then I'm going to tell it the map to from. I'm going to tell it explicitly because I have to because they're NumPy arrays. I'm going to tell it explicitly when you enter the construct, map in the U and the UTemp arrays. And it keeps track of the addresses so it picks up the swap. So that's it. What could be easier? And I get on an NVIDIA, I get amazing performance on an NVIDIA V100 of 22.6 seconds. Cool, right? No, not right. That performance sucks. Okay. I expect a little bit more out of going to a GPU. And of course, what's going on is if you think about it, if I'm moving those arrays, each and every time I call that loop nest, each step I'm taking two n squared size of type bytes that I'm moving back and forth. Now, this is important, and it's a general rule of GPU programming is it's really, really easy to say split up your loop. The hard part of GPU programming is thinking about how does your data movement align around that index space. And that's true regardless of OpenMP, SYCL, CUDA, I don't care. The real work is thinking about your data. And so what we've added in OpenMP is the idea of a target data region. And so it's just basically the idea is that I can define the data layout in GPU memory from the host. So I can move my arrays onto them once with the target entered data, and then the map clause tells you to map it to the device. And then when I'm all done, I once pull back the data I want with a target exit data map. So now I'm moving the data once on the device and once off of the device. If I do that, I get it down to 1.2 seconds. So a dramatic, dramatic improvement. And this, as I said, if I was doing a lecture on CUDA, we'd do exactly the same thing. I'd show you that. Here's the naive. This is what you get. Oh, now let's think about data movement. And just for the record, there's an awful lot I can do additionally to improve the performance of this. So by the time I'm done, we would have it down to under 0.1 seconds. So a lot more performance on the table. But come to the SC25 tutorial, Programming Your GPU with OpenMP, to learn more. So got to start advertising that. I'm going to skip that slide because of time, but it just shows more performance results, that it's not just our hokey little stencil code. So I think we hit our target on performance. Now, it has to be ubiquitous. It has to be everywhere. And what I want to emphasize, and I'm way low on time, so I'm gonna leave this to the backup that you can get off the slides. But what I want you to see from this is we built PyOMP around the Numba ecosystem and for both the CPU and the GPU. And I'm not going to walk through the details of this slide because the real point I want to leave you with, because I'm really running out of time, is we're layered on top of the standard off-the-shelf Numba compiler toolkit. That's key. So as new versions of Numba come out, we may not need to do anything. If we do, it'd just be a little tiny tweak because we piggyback off the existing Numba ecosystem. And one of the members of our team, Stuart, is an insider in Numba. Actually, so is Todd Anderson. So we are deeply, deeply connected to the Numba community and the LLVM community. So we're built very closely on those. And that's key because as they evolve, we doing next to nothing, in many cases, nothing, just carry right along with it. So we run on Linux 64, the Macs for the ARM 64. We run on on Linux on the PPC, x86. Um, so we're all over in the CPU space. In the GPU space, we're NVIDIA only, and I'll say a moment about that shorter. So to install, it's built right into the Conda system as a package. So there's the line to install it. We are working on a pip install. I don't do this work. Someone else in the team does. I think Stuart does. Um, and it's a hefty amount of work to use the PyPy package installer, but we're getting there. We're close. And everything's open source, everything. So there's the URL for getting everything open source. So I give us a check minus on being ubiquitous. And here's the thing. NVIDIA, bless their hearts, work very, very closely with Numba. NVIDIA recognizes that the Python community is important. Let's face it, it's one of the most important, if not the most important language in AI. And NVIDIA likes AI. So we basically did next to nothing to just, supporting the GPU was not a heavy lift for us because NVIDIA is all over the Numba ecosystem. AMD isn't. And the GPUs embedded on your laptops aren't. So right now, the GPU code only works for NVIDIA. So that's why it's the check minus. Now, we don't think it will take much at all to support AMD. We think this mapping into the HIP environment will be very easy, but that's engineering that hasn't happened yet. And we're right now this summer refactoring the software so it'll be much, much easier to support other devices. But I'm giving us a check minus because NVIDIA may be the number one GPU vendor for HPC, but there are others, and over time there will be even more. So stay tuned. I'm hoping we have something to announce maybe before the end of the year. Fingers crossed, that we'll have it. Okay. I'm now moving into the closing, and I want to tell you why PyOpenMP is far, far, far more important than you think. And I really need you to start using it. Here's why. And we're going to do a walk back in history. This is a slide. Some of you have seen my other presentations. Have probably seen this slide before. It's an exercise I did in the 90s. Is I basically went through conference proceedings over several years. This was done in the mid to late 80s. And wrote down every single programming model I heard mentioned in the research community. And this is what I came up with. And I'm sure if I spent more time and did a more careful literature search, I would have come up with even more. And, one can say, so what's the problem if we have a lot of different ways? We're obsessed with finding the right parallel programming environment. So there'll be a lot of them. That's a good thing, right? No, not really. And there's a study, I talk about this a lot. So once again, I apologize if you've seen it before, but if you haven't, you really need to pay very close attention. This is a study done at Stanford. And they picked a grocery store in Palo Alto, which is where Stanford people and rich Silicon Valley people live. And it's a gourmet grocery store, the Draeger grocery store. And so this professor trained the graduate students in their group to dress up and pretend to be representatives of a jam company. And they had one display with 24 jars of jam and another display with 6 jars of jam. And they invited people to sample the jams. And if they wanted, they were given a coupon for a discount to buy. So what this meant is they could track how many people walked by the display, how many people stopped and sampled a jam, and how many people subsequently purchased. And this is a very heavily cited and incredibly important study. So what they found, not surprisingly, is 60% of the people walking by the display sampled it when there were 24 jars, big, splashy, yes, try our jam, as opposed to the small 6 jar. But here's the number that just blew people away. Um, of the people that tried the jams with the 24 jar, only 3% made a purchase. Whereas for the 6 jar, 30% did. This is the study that singled out the phenomena that all of us humans are susceptible to. It's called choice overload. That a human being, when given too many choices, will choose not to choose. And this has now completely changed the retail space of how we market things. It applies not just to things like jams, it applies to retirement plans. This is part of being human. We just don't like too much choice. It's called choice overload. And so now, thinking about choice overload, what do you think this list accomplished? What do you think the result was to people new to parallel programming, thinking of jumping in and doing parallel computing, and they're presented with a list like this? What do you think it accomplishes? It's very damaging. It really hurt our ability to grow the parallel computing community. Furthermore, and this one's extremely important as well. I spent the last 30 years of my official career working for Intel, so working as a vendor. And I'm telling you, it's a zero-sum game. If I'm assigning engineers to chasing Falcon or P++, or, because this customer asked for it, I'm not spending engineering resources on making the base technologies better. So by forcing the vendors to run around in circles, it actually decreased the quality of what we had to work with. Now, what happened for those of you, especially those of you who are a little bit on the younger side, who may not know this history, in the early 90s, the HPC community, the programmer community, not the vendors, got fed up by the fact that every time I moved to another cluster or another commercial grade parallel machine, I had to learn a new message passing environment. And it was frustrating. You didn't gain anything intellectually from recoding all your message passing, and it just was a mess. So we got together and worked very, very hard in the early 90s to define a common message passing interface. And that, of course, led to MPI. But I can't stress enough, the primary drivers were the academic research community. The vendors jumped in and supported, but it was driven first and foremost by the application developers who had to write and support code. And then later in the 90s, a version of this happened again with the sociological factor is there was a funding mechanism in the United States where much of the money in HPC was channeled through this one program, the ASCII program. And so the application developers in that program used their power of purchasing by saying we would only buy machines that supported an open multi-threading environment that you vendors who want to sell into our program will work with us to create. So it was application user driven that gave us OpenMP. And I can't emphasize that enough. The people who write application software are the ones who were hurt by churn on different programming models. And they have to use their power because, of course, all of these machines are useless without applications. Applications people, if they join together, as happened in MPI and has happened in OpenMP, have a huge amount of power. And so we came out of the 90s with this grand convergence, and it's largely held today. If I was talking to you face to face and you're all in the room, I'd say, everyone, raise your hand if you've used a message passing environment other than MPI. And there'd be very few hands raised. Similarly, you're writing multi-threaded code as an application programmer. How many have used something other than OpenMP? It's just like they are dominant. So we really are great there. We're screwed on GPUs a bit because there's CUDA, OpenCL, SYCL, this abomination OpenACC, which none of you should ever use. There's now OpenMP. So we have more work to do on the GPU front. It's particularly sad on the GPU because if you look at what they're doing under the covers, they're doing the same things. There's no reason we have this crazy diversity. Now, here is why I'm so passionate about this. And now I'm talking to those of you who are really, really focused on Python and parallel computing. Because here's the list. I went online, the references at the bottom of the slide, and I added a few. Here's a list of parallel programming with Python and how horribly, horribly fragmented it is. As we learned in the 90s with parallel computing in C, Fortran, and C++, this diversity is damaging. It's bad. We need to converge around order a single digit, three to five, no more than five, a small number. And the only way history tells us the only way this is going to happen is if the people writing the applications take charge. Because as I said, the vendor community who have the money, they depend on you. They just don't want you to realize it. So I'm calling for a revolution. Yes, I am. I'm calling for a revolution. I'm retired now. Intel can't fire me because I already left. So you need to pull together the applications community, find the right organizational structure to make it happen, and pick a few of these to work on and make the ubiquitous standard. Uh, and for HPC, you need a single model that spans the CPU and the GPU, which is why I think you need OpenMP. It's why you need PyOMP. But I will be honest, if you came back and said, no, 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 we, the application community together, have converged around these three models and it's not PyOMP, I would grumble. I might even shed a few tears. But I'd prefer that to this craziness. So I'm really depending on you folks to pull together whatever structures, whatever organizations you can. There's a big sociological factor to converging around a small number of parallel programming models. And please consider PyOMP because it's really, really cool. So this is the last slide. Um, I'm just kind of summarizing. We all know the future is Python. I'm sorry, C, Fortran programmers, you're going away. And, okay, no, there'll always be a need for a little bit of C, and Fortran, but more and more it'll be hidden behind a Python API. I mean, one of the reasons Python is so powerful is it's relatively straightforward to wrap C with Python. Um, PyOMP by design lets you take what you already know about OpenMP and just immediately import it into Python. So for the HPC community, I really think PyOMP is going to be a hit. It's wonderful. All right, but now we need your help. All right. The one thing PyOMP doesn't have is a user base. Okay, it's relatively new. So we need people in HPC to start using it and to start telling us what works and what doesn't work. And I will come anywhere virtually, or if you'll pay my travel costs, I'll go anywhere in person and I will give talks and tutorials and hands-on teaching. I want to build a user base around PyOMP. So, and I want to hear about your successes, but I also want to hear about your failures. Because we're not perfect, it's entirely possible we make mistakes. The second point, and this really is so important, I cannot stress enough. You, the community of HPC Python programmers, you got to drive a convergence around a small number of options. You have to. If you don't do it, things are going to stay immature and craziness. And then final, and this is more for the vendor community, but also academic communities doing research in parallel programming models. We need to grow the engineering team and the research team contributing to PyOMP. It's four of us right now. It needs to be bigger, And I mentioned in particular, there's this construct that has very little visibility in OpenMP called the work-share construct. That combined with fusion and array elision would give us a great addition to array-style programming. So, any rate, I guess that finishes my talk. And I always like to finish with a beautiful picture of a kayak. That is a kayak I built myself. It is an Inuit Greenlandic skin-on-frame kayak, and it is utterly beautiful. But we're not here to talk about kayaking, are we? So I'll stop.
Okay, thank you so much, Tim. It was a pleasure as usual to listen to you. Um, okay, so we got already a few questions in. Let me start from the top. Does multi-CPU, does multi-GPU work? That means does OMP set default device work?
I personally have not tested it, but knowing the way PyOpenMP is built, it works. Or if it doesn't work, it would be a trivial patch, but I'm pretty sure it works.
In that regard, is the whole set of OpenMP constructs and functions supported or only a subset?
Only as let me be clear. I'm going to say only a subset, but it's most of 4.5. A lot of it comes down to there's only 4 of us, and I'm not going to tell you something works that I haven't explicitly tested. But because basically what we do is we map the string in the with context onto the LLVM backend. So if LLVM supports it, then we support it. Now, what that means is we don't support 6.0 because no one does. It's too new. This is one of my complaints about the OpenMP community is the language design is so far out ahead of implementation, and it causes a lot of confusion and frustration. I really liked the rule we had in OpenCL, another language standard I worked on, and comes from the Kronos organization, which is you never release a spec until you have at least 2 complete implementations. And I really wish the OpenMP people did that as well. So LLVM doesn't support 6.0, so we don't support it. But there is no reason we can't, and we should be able to support anything that's in the LLVM, which is, up through 5.2. But I want to be
Perfect.
really honest, I haven't tested it, so
Okay. There's actually one interesting comment you probably will be happy to hear. So someone, while you're talking, tried pip install PyOMP, and it worked, and he had it installed in his computers while we were talking.
wow, that's funny. I didn't know we had that nailed down yet. That's awesome. Okay, cool.
Yeah. Someone else asked, can you have the slides, please? I can answer that yes. This talk will be recorded. It will show up on the POP YouTube channel, and the slides will be attached to that. And once everything is available, the recording and the slides, I will send out a mail to everyone notifying.
And I want to emphasize with the slides, so there's a philosophical argument about the purpose of slides. Are they to support the speaker or are they briefing documents? I believe they're briefing documents. You can follow, that's why I tend to have wordy slides. And I have an appendix which walks through, it's taken from my PyOMP tutorial, but it's basically a much slower walkthrough of PyOMP where I spend more time explaining each of the OpenMP isms. So there's a long backup section for those of you who the pace through the OpenMP was too fast. So keep in mind there'll be a lot more in the slides than just what I talked about.
Okay. There was an additional comment actually that the same person who successfully used pip install PyOMP also tried the Conda install, and that didn't work. And in the chat, you can also access, there's probably some error message you can find. Yeah, then another question, does anyone know if there's a performance comparison paper or anything that compares PyComp SS and PyOMP?
Um, we have not done detailed benchmarking against the others. There has been some benchmarking done. I didn't do it, so I don't know the answer. I think, oh, I'll just say no. I don't know.
Yeah.
That's the right answer. If Todd Anderson or Georges were here, they've spent some time comparing to others. So, but my feeling is that the primary point of comparison should be C. And if I'm hitting C, then I don't think anyone's going to beat us. But no, we have not done a detailed benchmarking study. And I want to emphasize, I'm a real stickler for how you benchmark. So when we are ready to do the benchmarking study, the way I will do it is I will contact the people involved with those other systems, and we will collaborate on a paper that we are all authors of, and we will go over each other's work and run on the same physical hardware. It's very painstaking and difficult, but that's the honest, polite way to benchmark. And so that paper will come at some point, but it hasn't been done yet.
And then there's an interesting, not Python or PyOMP related question, but I still will ask it because I think you are the person who can answer it. Why can't we have a Pragma-based API for distributed memory programming?
Oh my gosh. Great
MPI
question.
is painful.
I love MPI. What do you mean? It's not painful. It's great. We did a great job with MPI. All right. So we tried that. In fact,
I know,
Intel
yeah.
had a product called Cluster OpenMP. This was early 2000s. And it was built on, for those of you who are, deeply steeped in the ancient literature of computer science, it was built on Treadmarks, um, which is a distributed multi-threading environment. Here's the problem is, first off, intellectually, there's no reason in principle you couldn't have a distributed memory directive-driven API. We did it with Cluster OpenMP. The performance was utterly abysmal, so bad that we just dropped that whole research direction. And here's why. Um, the granularity of data sharing was wrong. Because if you're going to have a directive-driven scheme, you have to deal with the scope of data sharing. And that only way we could figure out how to do that was page-based. And for performance, page-based is the wrong granularity. So for a directive-driven message passing, you're going to have to think much, much harder about how you manage the level of data sharing. That's the hard part. Now, the right way to do it, and I did a lot of research. In fact, if I was still at Intel, this would be my primary research effort, is what if you took all of the complexity of the message passing and I hid it behind a distributed data structure API. And to get an idea, because we don't have 45 minutes for another talk, look at the package global arrays, or GA. It's an existing package. It's totally cool. And it builds on this concept I just pointed out, which is if you say, I know my work is going to use this set of distributed data structures, I can hide most of the message passing inside the distributed data structure. So then I do everything through a one-sided communication. I put get, and all of the details that makes MPI so much fun for weird people like me is hidden. So the right way to do it is not directives. The right way to do it is to focus on distributed data structures. And a proof point of that is the package global arrays, which has been very heavily used for almost 3 decades in the computational chemistry world.
Okay. Any more last questions? You can also raise your hand or something if you want to speak up if you are too lazy to type the question in. Looks like everyone is happy. So thanks so much again, Tim, for spending the time with us and yeah, telling us about PyOMP. Like Tim, I invite everyone to try it out. Send lots of bug reports to the team uh, so we can improve it. And yeah, and the next thing is the revolution on the either Pi program models or GPU program models by the users, I guess. Yeah. Okay. Thanks again, everybody, and hereby, yeah. I was sending. Have a good weekend, but it's only Monday. I'm sorry. Yeah. Enjoy the rest of the day, especially if you're in the time zone, which is early. Otherwise, have a good afternoon and see you next time in our next POP webinar. Thank you.